Hello, everyone, and welcome to today's webinar presentation, An Introduction to App Hardening. Before we get started, I have a few housekeeping items to go over. First, all attendees will be muted, so we invite you to submit any questions into the Q&A chat section, and we will go through them once the presentation concludes. If we do not have enough time to get to your question, we will follow up separately. We will also be sharing out the on-demand version of today's presentation, so be sure to check your inbox for that. Now, I would like to introduce you to our presenter, Guardsquare pre-sales engineer, Jonas Jailbreak. Jonas is responsible for educating and building awareness within the mobile app security landscape. In addition to his knowledge sharing, he assists developers with the integration and configuration of Guardsquare mobile app security solutions. Jonas holds a master's degree in engineering technology with a focus in electronics. And with that, I would like to turn it over to Jonas to begin today's presentation.
Thank you, Lauren, and nice to meet you all. So during this webinar, we will cover the current mobile threat landscape. We will also take a look at some concrete case studies, followed by some do-it-yourself implementations for jailbroken device checking or root checking, as well as the verification on debuggers. We will also cover what the current issues are with these do-it-yourself implementations. So let's take a look at the current mobile threat landscape. There are three main categories of mobile threats. So sometimes they can also refer to two categories. Let me dive into more details later on. So a first category are the static analysis attacks. So there a malicious user or a reverse engineer is going to decompile your application or SDK on his own local machine. He might try to take a look at your source code, try to disassemble it and understand what's going on there. Once he has done that, he might try to spot any vulnerabilities, patch certain security checks out, for example, bypass license checks, and so on. On a dynamic attack, there the malicious user is going to run your application on a test device. That gives certain advantages. For example, he can connect debuggers to the device. He can also try to hook certain implementations and change the behavior of these methods in a dynamic way. For example, make license checks always return true. Another category are the network attacks. These are sometimes also considered to be part of the dynamic attacks, since it's necessary to run the app on a test device. So during a network attack, the malicious user is going to perform a so-called man-in-the-middle attack. It can be on an end user's device to sniff their login credentials, for example, but he can also do that on his own device to get a better understanding on how the API between your app and your backend works. These mobile threats can come from anywhere. There might be malware installed on the device, but also keyloggers or spyware may be present that try to sniff the data that the user enters into your application. Besides malware, keyloggers, and spyware, also malicious users or reverse engineers might try to decompile or interact with the app themselves in a way that they are not supposed to interact with it. So the parts that you wish to protect in your application, or the vulnerable parts, are of course the intellectual property, stored keys. Think about API keys, but also cryptographic keys that you use to encrypt or decrypt certain things. Also, the authentication mechanism might be a target for these malicious users. Of course, it's the secure communication between your app and your backend. All the advertisements. So people might try to change the advertisements in such a way that the profit of those ads are routed to the attacker rather than your company. Of course, if you choose to show advertisements to your customers, of course you want to benefit from that, and it's not really desired that the profit of these ads go to different people. So let's take a better look at the static analysis. So various tools to decompile an application exist out of there. So for example, on Android, you can simply use Android Studio to decompile an application and look at the source code, the bytecode inside that APK. We will see an example on that in the next slide. Also other tools, think about APK tool, DexDump, but also commercial tools like Hopper, IDA Pro are available out there to decompile applications. I would highly recommend that you try out these different tools on your own application and take a look for yourself to see if any security sensitive information is available in there. Here we can see Android Studio decompiling an application. This time it was an open source application. If I recall correctly, the Google Play Service app, the wallet module in there. So here you can see that you can navigate through all these packages, and if the class names are not obfuscated, it's really easy to recognize what these methods and classes are doing. For example, as you can see in this proxy card class, there are some security sensitive methods in there. Think about the get CVN, get expiration month, and get expiration year methods. For dynamic attacks, it is necessary to have a test device available, either an Android phone or an iPhone, to run the application. During a dynamic analysis, the malicious user can attach a debugger to your application to get the memory dump, for example, but he can also hook the application using Frida, exposed, fishhook, or other tools to change the implementation of certain methods. For example, if you have any premium features available in your application, the malicious user might try to hook these premium checks and will change them in such a way that these will always return true or indicate that they are a premium user, even if they didn't pay for your particular application or premium feature set. Let's take a look at some case studies we have set up. For example, API key extraction, how would that work specifically? First of all, the attacker would need to download the application to his device. In case he is using an iDevice, he will need to decrypt the IPA first using a jailbroken device in order to examine the app in more detail. Once that's done, he can navigate through the source code. He can search, for example, for keywords like API to see if any keys pop up. If he finds such a key, he can extract this and use it in his own application to make use of maybe a paid service your company is paying for. These services often charge you money depending on the amount of requests that you perform every month or year. And now imagine if these attackers are going to distribute these APKs, these API keys, my apologies. Of course, that will result in a loss of money for your company, since your company gets charged of the usage of these keys. Another thing that can happen is that the malicious user inserts any malware inside your application. It can be done to create a botnet, for example, and to perform a DDoS attack on certain servers. In case the attacker wishes to accomplish something like this, you again, of course, needs to download the application, modify it in such a way that the botnet code is injected in the application and distributed as a clone. Your legitimate users might be tricked into believing that the clone is the actual app. They will be using that app, and without them knowing, they are actually becoming part of the botnet of the attacker. The attacker might also want to modify your application in such a way that he can harvest legitimate users and credentials. Think, for example, you have a video streaming services for which you charge money to your users every month. If an attacker downloads your app and changes it in such a way that instead of logging your users in, the credentials will actually get sent to his own backend server. From there on, he can access these login credentials, and he can, of course, make use of your service for free. But even worse, he might also distribute these login credentials for other people to enjoy. Of course, we can argue that these are just drawn examples, and well, we don't know if this would actually happen in real life. Well, for that, we also selected some examples on applications that were actually attacked. If you would Google these names of these particular apps coming up in the next couple of slides, you'll notice that these articles are available for free. They will explain in a lot of detail what the malicious users did, often just for fun or to prove their skill, and you'll see that or what the exact vulnerabilities with these applications were. In this example, we have two apps. There is the PhotoVault app and the KeepSafe application. Both apps have a similar feature set, so they try protect certain pictures on the phone. In case you lose your phone, you would need to provide a second passcode in order to get access to these images or pictures that you have stored in their vaults. Now, actually, it seems after reverse engineering these applications that the passcode the user set for these apps is actually stored in a very unsecure way. It's stored in plain text, so using a jailbroken device, you can easily navigate through the directories of these applications, and you gain access to the password in plain text. Besides that, these applications also didn't implement any hooking protection. So using a tool like Frida, or in this example, script, you can just call the dismiss lock screen method that's part of this interface, and that would just make the passcode interface disappear as if the passcode was entered correctly. So what went wrong here? Obviously, there was no strong protection against static analysis that gave the advantages to the attackers to quickly find methods like dismiss lock screen. If they would have been renamed to a random name such as ABC, then it wasn't really clear anymore what that bot was particularly doing. Besides that, also no protection against hooking or swizzling was implemented, making it possible to use tools like Frida or Script. And on top of that, also the password wasn't even stored in a secure encrypted way. In general, you could summarize that by saying there was no multi-layered protection. Another example on Android phones this time is Pokemon Go. So Pokemon Go, a lot of you will probably know that game. In order to play it, you need to walk through a city and capture different Pokemons. However, a lot of cheaters also played the game just from their couch. They didn't really walk around, and they used rooted phones in order to, well, create some kind of a joystick in the application and use that joystick to move around the town instead of really walking. Of course, the developers of Pokemon Go didn't really like that, so they implemented a very basic do-it-yourself root check to verify if the device is rooted. If the device was rooted, they could simply exit the application and the user couldn't play the game anymore. But since it's just a really basic implementation, it was actually possible for these cheaters to simply use open source tools available like RootGlobe or Magisk Hide, which will actually hide the rooting of the device in quite a clever way, and you could easily bypass this mechanism that Pokemon Go implemented. So what went wrong here? Of course, there was no root hiding detection techniques available, and also there was no hooking protection, because these tools heavily rely on hooking, and if they would have somehow implemented a protection against that, that would also prevent you from using those tools. So again, you could summarize it as no multi-layered approach was taken. Another example, also on Android, is the 7Pay app. So 7Pay got hacked. At the moment, it is not really clear what exactly happened, but a lot of people lost a lot of money using that app. So some scenarios that could have taken place was maybe a clone of the application got distributed, and that clone was used to harvest credentials of these particular 900 users. Another option is that people performed a man-in-the-middle attack. Doing that, they could sniff the credentials of the users while they were logging in on unsecure networks, for example. A third option is an overlay attack, which can be used to sniff the data that the user enters on the keyboard while logging in, and then again hijacking the accounts. So in these three scenarios, what would have gone wrong? Well, obviously there wouldn't be a tampering detection check because if that would detect a clone, then you can simply exit the application. Also, maybe no communication hardening was in place, making man-in-the-middle attacks possible. Or maybe just there wasn't just any protection against overlay or keyloggers, making it possible for people to sniff the end user's credentials through an overlay attack. Again, just as with the other two examples, we could summarize that no multi-layered approach was taken. A fourth example is the popular messaging app WhatsApp. This example is actually, this attack was actually performed on both iOS and Android, and malicious users inserted commercial spyware in the application that made it possible for the attackers to access the microphone, camera, messages, emails, and even location data of the users of WhatsApp. Of course, if that happens to your company, especially if you're that huge as WhatsApp, that's a disaster. It destroys the trust your users have in your application, and it can result in people abandoning your app. So what went wrong here? There was no tampering detection preventing modified apps from running. Also, there was no code integrity protection, which could give malware the opportunity to interact with the code in a dynamic way, for example, by hooking. Again, we could summarize this as no multi-layered approach was taken. So what you can do to defend against different of these threats, you can browse the internet and you can search for these do-it-yourself implementations in order to, for example, defend against jailbroken or rooted devices or debuggers. The next couple of slides, we're going to give you an indication why that wouldn't be the best approach to take. So if you would search, for example, the web for a jailbreak detection snippet, one you are going to come across very often is the one you can see here on the left-hand side of this slide. This jailbreak detection function will actually try to open up a shell with root access. And if that succeeds, then that's of course a clear indication that the device your app is running on is jailbroken. You could then implement a response, like you could limit the feature set, or you can implement a crash if you detect this. However, the problem with this, it's a really basic check. It's really well known to both developers, but also to malicious users. It is also not inlined, and it looks always the same. On the right-hand side, you can see a snippet and what we can use to bypass this jailbreak detection technique. So what we're going to do is we're going to hook the system function, you're calling here on the left-hand side, and we're going to return the 0 value in every case, also if the device is jailbroken. Therefore, this check will be bypassed even on jailbroken devices. You can use a similar approach on Android. A common technique to detect if the device is rooted is by getting the environment variable path and see if any presence of SU, SuperSU, BusyBox, or any other malicious apps is in there that indicates that the device is rooted. So again, a very easy countermeasure to such an implementation is by hooking the get environment method of the system library and just return or removing these keywords from the results. So in this example, SU, BusyBox, SuperSU, superuser.apk, and so on are all removed from the results. This is actually a technique that's being used by the open source application root cloak in order to hide the root for applications that are implementing such a root check. So also for debugger detection, there is a wide variety on do-it-yourself implementations that you can find on the internet. One of them is this one you can see here on the left-hand side. So we're going to search for any, we're going to search for ptrace in particularly, and if we find a ptrace, then we're going to send a ptrace deny attach instruction. Now again, by just hooking the DLSIM method, you can easily return a fake ptrace, and that will allow you to still be able to debug this particular iOS application. On Android, there is a debug.isDebugger connected method available that will return true if a debugger is connected. But again, it's very easy to just hook that particular method and make it always return false, even though there is a debugger attached. So how can you defend against these different threats? So here at Guardsquare, we do offer 3 solutions, of which 2 are code hardening solutions. The first one is DexCard. That solution will harden your Android apps. DexCard consists of a RASP feature set to protect your application against dynamic attacks such as rooted devices, debuggers, hooking, tampering, emulators, and so on. We support languages like Java, Kotlin, but we also do support hybrid setups. Think about apps written with Cordova, Ionic, or React Native, and also Unity games. DexCard also consists of an obfuscation feature set, so simple name obfuscation is available here, but also more advanced techniques of obfuscation. Think about arithmetic obfuscation, control flow obfuscation, class encryption, string encryption, and so on. We also offer an SSL pinning implementation. And finally, as an icing on the cake, we also offer shrinking and optimization. With these last 2 steps, we can actually reduce the net size of your application by 5 to 70% and increase the net speed by 10 to 20%, even though we applied all the obfuscation and all the security features to your code. DexCard is backwards compatible with our open source Java optimizer ProGuard. So if you have already developed any keep rules for ProGuard, you can simply reuse those in DexCard as well. The integration effort for complete new users takes about up to 2 to 3 weeks. It's a bit faster for people who are used to working with, for example, ProGuard. DexCard integrates in the build process as a Cradle plugin. On the dynamic checks, you had the choice at the moment. Today we released our version 8.7, which gives you the opportunity to, well, make use of a runtime library to verify these different dynamic threats. But we can also inject checks for these threats randomly through your code. By default, we make the application crash if we detect the threat, but you can use a callback instead if you want to implement a custom response. DexCard, our tool to harden your iOS apps, has a very similar philosophy, but of course, since the operating systems are entirely different, we need to use different techniques to protect against these same threats. We have a RASP feature set available, defending your application against any dynamic attacks. And besides that, we also offer various techniques of obfuscation to make static analysis more complicated. DexCard, in contrast to DexCard, doesn't really integrate in the build process. It's shipped as a command line tool. It will take your app or SDK as an input together with a configuration file, and it will produce a protected SDK or app as an output. Again, we support the native builds in Objective-C and Swift, but also hybrid builds such as Cordova, React Native, and Unity apps. We do have 2 requirements for you if you wish to use DexCard. You need to use Xcode 10 or later, and bitcode should be enabled for your own source code and preferably as much libraries as possible. The performance overhead is generally not noticeable if you don't over-obfuscate the application, and the integration effort, just as with DexCard, takes about up to 2 to 3 weeks. A last tool we have available here at Guardsquare is Threatcast. Threatcast isn't a code hardening tool. It is a monitoring tool that will report you against any threats on the dynamic side in real time. For example, if somebody runs your application on a jailbroken device, or if somebody tries to tamper with it, it gets reported to our cloud server Threatcast, and there you can, after logging in, of course, analyze all that data available. We monitor threats regarding the environment integrity, the application integrity, and the code integrity. And you have different views here available. For example, you can display the threats in a simple list, a timeline, or on a roadmap. You can, by using the roadmap, you can see on where the threats are coming from and what countries are the hotspots or where the most threats are coming from. Of course, it's important to mention that we only keep track of country data there. We do not store any city names or street names. Integrating Threatcast is super easy. It's just, well, mentioning the API key in either the DexCard or IXCard configuration file. From there on, the tools will know what to do with that and integrate the API calls for you. So that's it for our webinar. If there are any questions, please don't hesitate to ask them.
Thank you for that presentation, Jonas. We did receive a few questions. So question 1, would DexCard prevent reverse advanced tools, if any?
Yes, DexCard can prevent most or prevent reverse engineering with with all of the tools. So we use a multi-layered approach here. You can see every different feature as a separate layer. So the more features you enable, the more layers you enable on top of the security sensitive parts of your application. Of course, the more secure it gets. It is important to mention that it's code hardening. So in the end, reverse engineering is theoretically always possible, but of course it will become very, very difficult to do so, especially if you integrate it very well.
Do you offer SSL pinning on iOS?
No, we do not offer SSL pinning on iOS. The reason for that is because Apple already offers that by default, but we do harden that implementation by providing hooking detection, for example, so that malicious users can't disable the SSL pinning features you have available in your app.
DexCard Signals, which can help crash if something is tampered with. Can you share some more details around that?
Sorry, can you repeat that question?
Yep. DexCard Signals, which can help an application crash if something is tampered with. Can you share more details about that process?
So at the moment, you do have two choices with DexCard. If you develop, at least if you're developing an application, so you can make DexCard inject checks against tampering that consist out of three main parts. So we can detect if the app is repacked, for example, or if different development signing certificates are used to re-sign the application. And lastly, there is also a file checker available that can check the integrity on certain files you have listed yourself. So you can mention which checks you want to enable in the configuration file, and in that case they will be injected at randomly through your application, and by default a crash will occur if a threat against that is detected. If the crash is not desired, you can mention a callback function instead, and then that function will be executed instead of the randomized crash. If you develop an SDK, you need to use the runtime library. The runtime library is also still available for app developers. And using the runtime library, you can actually achieve the same. So here you would call the tamper detector.checkAPK, for example, to verify if the app is repacked. And you will get basically a Boolean value that indicates whether or not the app has been tampered with. Based on that Boolean value, you can then implement your own response, which can be a crash, but you can also choose to use a different approach. For example, limit the feature set.
For the app to utilize Threatcast, it has to communicate to the internet at all times?
No, not necessarily. With Threatcast, you have the choice to send periodic heartbeats to the cloud. That means that every active user is going to send one heartbeat or one signal a day to our cloud platform. Why do we do that? That can be used to count the daily active users, and for you that can be interesting information to to compare the amount of daily active users to the amount of threats that you are receiving. Besides these heartbeats, we only send data to the cloud once we detect a threat. So if somebody, for example, hooks your application, then that will be sent together with some information on the device. Think about the operating system, the device brand, model, the time, and so on.
Do you offer optimization or shrinking on iOS applications?
No, the CDLang compiler of Apple is already very efficient, so there is not a lot for us to optimize anymore compared to Android.
Can I include a trial version of DexCard library in an Android Studio build process?
I'm not sure I fully understand that question. You can include a library that's protected with DexCard inside another project. That's not a problem at all. If that answers the question, of course.
In the integration effort, you listed both DexCard and IXGuard 2 to 3 weeks. In your own experience, what is the longest and shortest integration process that you have experienced?
That's a good question. On the longest integration, I would say maybe around 4 weeks. I have experienced at least. The shortest, I think it can be done in a matter of days if you're really used to the tools and used to the project you need to obfuscate, of course.
When integrating a solution, what is the most difficult thing to do?
The most difficult parts will be it's actually a bit of a different story for Android and iOS. Let's cover Android first. So there, the main issue will be the reflection. So name obfuscation will break your app where it relies on reflection. You may be used to that if you're a ProGuard user. In order to prevent your app from crashing on these places, you need to add these blacklists or keep rules to exclude those parts of being renamed. Besides that, there is also the optimization and shrinking step that sometimes get tricked into believing that certain resources or code aren't really used, and therefore they get removed during the build process. Just as with name obfuscation, it can then be tackled with these different keep rules. You need to blacklist those parts of code from being optimized or shrunken. And once that's done, actually the hardest part is covered. From there on, you need to apply the additional hardening features, but that's just enabling them in your configuration file and referring to the correct class paths for which you wish to enable certain features. On iOS, the most time will be in configuring the name obfuscation, just as with DexCard. There the app will break where it relies on reflection if name obfuscation is applied, so you need to assemble these blacklists to prevent IXGuard from renaming those parts. Besides that, there is also the method call lowering feature that will defend your application against swizzling. Of course, as a developer, you can rely on swizzling yourself. So again, those parts need to be blacklisted for that particular feature, and that can also take some time. For name obfuscation, we have an auto configuration tool in both products, which will actually give you some suggestions and help you set up these blacklists. The way it works, for example, on Android, you connect a test device to the computer, you run through all the functionality of your application, and it will print out some suggestions on keep rules to the logcat. From there, you can copy paste these to the configuration file. On iOS, it works with an in-app assistant, but the approach is very similarly.
Do you have any use cases to integrate CI or CD process?
We have a lot of users using a CI/CD system. For example, Jenkins is a widely used CI/CD system. Integrating is most of the time very easy because DexCard just integrates in the build process, so there isn't a lot more to do than changing the builds.gradle files. For IXGuard, that tool can be launched from one single command, so you can simply run a script at the end of the build process to start IXGuard in order to integrate it in your CI/CD system.
Regarding hook protection, is it already implemented for any hook, or should I point out the methods that I want to protect?
That's again a different story on Android and iOS. So on Android, if you're going to use the runtime library, then these checks, well, they are where you place them in the code. Personally, I would recommend that at the beginning of the application's execution, as well as before every secure operation. If you choose to use the automated injection, then you can, well, they will actually be sprayed randomly through the code. On iOS, they are by default randomly sprayed through the code, and they are also injected in the entry point functions so that we can detect hooking before any user interaction with the app is even possible. On top of that, you can also set certain checkpoints. By doing that, IXGuard will make sure to inject a check there as well for hooking.
Perfect. And our final question, can DexCard protect communication between apps?
That's a good question. It can detect if malware is interacting with an application, for example, by hooking certain things, but just regular communication, if that would be allowed by the developers, that's something we do not detect.
Perfect. So that concludes our presentation for today. I thank you all for joining us. And as I mentioned in the beginning, we will be sharing out the recording of this webinar. Thank you and have a great rest of your day.